Okay, chapter 3. All right. Um, okay, we're going to talk about acceleration. Acceleration is a rate of change of velocity per unit of time. Acceleration is a vector quantity. Okay, so it's v over t. All right. It says, what is the acceleration of a ball rolling from rest down a hill to a speed of 16 meters per second in 8 seconds? Okay. Now, what does delta mean again? Change. Change is final minus initial. Okay, write that down. Final minus initial is delta. Okay, so in this case, we have a ball rolling from rest to a speed of 16 meters per second. So our final speed is 16 meters per second. Our initial speed, 0. All right, 16 minus 0 is 0. Now, you notice that's going to be positive, right? Okay, positive acceleration because it's 16 minus 0. It's not the other way around. Like if it was rolling at 16 and then came to a rest, then it would be 0 minus 16 would be a negative acceleration, right? Divided by 8 seconds. Okay, so 16 over 8 is 2. Now look at the units here. Meters per second squared. All right, you have meters per second divided by seconds. Okay, and if you do that, meters per second divided by seconds, all right, this is equivalent to meters per second times 1 over seconds. That's how you get meters per second squared. Every year I get people that try to cancel these seconds out and left with meters. Acceleration is not a distance. It's acceleration. It's how fast or how slow the speed's changing. Okay? All right. Let's see what we got here. All right, you can calculate the distance traveled with a constant acceleration for the previous example using this formula. Now, I call this formula the distance formula. All right, distance equals initial velocity, that's VI, times the time, plus 1/2 acceleration times time squared. Now, since the ball was rolling from rest, it's 0 meters per second, so 0 times anything, 0, right? Plus 1/2 A is 2 meters per second squared, time is 8 seconds squared, okay? Now, so you have 1/2 times 2 is 1, right? And 1 times 8 squared is 64. So you get 64 meters. We can also calculate how fast the ball is going when it reaches the end of the hill if we were not given it. Okay, so if they didn't tell us that, if they said that the ball was rolling from rest, right? Okay, that's the initial velocity. With an acceleration of 2 for 8 seconds, we would get 16 meters per second. So if you have meters per second squared times seconds, seconds and the second squared cancel, so you just have meters per second. Okay? If you're given the time using this formula, all right, so if we give you the time, you can use this formula, VF equals VI plus AT. Okay? If you're not given time, and you have to remember this, I'll usually yell it out in class. If there's no time, then you use the VF squared formula because there's no time in there, but there's a distance. Okay? So if you were, this is VF squared, the final velocity squared equals the initial velocity squared, 0 squared 0, plus 2 times the acceleration times the distance traveled. All right? And then you have to take the square root. A lot of people, on a test, sometimes I'll give you this as a choice for an answer, 256, and you look, oh, I got it right. No, you didn't get it right. You didn't take the square root. You didn't finish the job. Okay? 16 meters per second. Okay? So that's how you do that. All right, now we're going to talk about velocity versus time graphs. Okay, last chapter we did distance versus time graphs, and the slope of a distance versus time graph was velocity. Okay? In a velocity versus time graph, the slope gives you acceleration and the area under the curve. All right, so like if I measured this here, this area here, this is a triangle, so that'd be 1/2 base times height. If it was a rectangle, like a line straight across, that would just be base times height. Okay, and that area will tell you how far it's traveled. Okay, it'll actually give you the displacement. All right, everything above the axes is positive, everything below the axes is negative. Okay, so this is going forward, this is going backwards. So here's an example here. You have a nice straight line, so it's constant, and the slope of velocity versus time is acceleration. So it's a positive acceleration. So that means you're going faster. Okay. And since it's above the axis, it's moving away from you. Okay. This one here, a horizontal line. That means there's no acceleration. So that means you're going constant speed in the positive direction because it's above the axis. If it was below the axis, it'd be negative direction, it'd be coming towards you. All right. Remember, positives going away from you, negatives coming towards you. Here's constant negative acceleration. So it's coming it's coming towards you, but it's slowing down. Okay? Because what's this right here? This is your velocity, all right, where it's zero. Okay, so it's slowing down, slowing down, slowing down. So it's like you're coming up to a stoplight. Okay? But you're still moving away from the source because it's up here. Now this one's an interesting one. This is a ball being thrown up and then falling down. Now, if I throw a ball up at 10 meters per second, it's going to go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop at the top. And then negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, 7, 8, 9, and finally negative 10. All right? So whatever speed I throw it up at, that is the speed it will be when it comes back down because it decelerates as it's going up and accelerates as it's coming down. So this graph here shows exactly that. Right here, it's going away from you at its maximum speed. Here, it's at the top, it's stopped. And then here, it's coming towards you with the same acceleration that it was decelerating at. Okay? And so this is where you'd catch it. Okay? Or if you could think of a swing or a pendulum, that would be where are you going fastest on a swing? Right at the bottom. Where do you stop? When you're out here. And then you come back. So that would be a person swinging from the bottom point outward because it's going away from you and then coming back down. All right. So if you're pushing a kid on a swing, that's what this graph would look like. Okay. All right. Acceleration versus time. The area under the curve for the graph will give you velocity. If I take the slope of this line, my units are meters per second cubed. There's no such thing. So taking the slope of an acceleration versus time graph is useless. We don't do it. It's only the area under the curve. And in this course, acceleration versus time will all be boxes. All right, they'll all be rectangles, base times height, because we deal with constant acceleration and constant deceleration. So here's constant acceleration going up. If I want to find out how fast it's going, all right, I would take the area under this curve right here. All right, if I want to know at this point, like 2 seconds, how fast is it going? I would just take that area. Okay. Here's zero acceleration. It's constant speed. It's at the zero. And this would be deceleration, constant deceleration. It's underneath the curve. Okay. That was it. That was the only 3 acceleration graphs that you're going to see this year. Okay. Remember, the area under the curve gives you velocity. For velocity versus time, the slope gives you acceleration. The area gives you distance traveled. All right. You're going to have to know that stuff. It's burn it into your brain. Okay. Make sure you're taking good notes on this. Okay. Watch the video a couple times. All right. It'll make more sense. All right. Now, let's look at this here. All right. If this is a distance versus time graph, okay, and I asked you what is happening from here to here, all right, tell me what's going on. All right. Say it out loud. See if you're right. It's curved. So this means it's moving away from you because it's going up and it's getting faster. So it's increasing speed or accelerating. Okay. What about this section here? It's a distance versus time graph. It's standing still, right? What about from here to here? This one, it's a straight line, so it's constant speed because it's the slope of speed, but because it's coming towards us, all right? Okay, so it's constant speed coming towards us. And then when it hits this spot here, where is it? it's at zero distance. So it's where we started, but now we're continually going backwards. All right. Okay. And then it stops. And then here it goes forward again, back to the origin at constant speed. So if I asked you to tell me a story of this little guy on his tricycle, what could something like that sound like? All right. Um, let's call this little guy Jimmy. All right. Jimmy's on his tricycle and he is on Gunther's Hill, and he lets go of his little feet here, and he just starts going down the hill faster and faster and faster and faster and faster until he goes so fast he hits a parked car. Boom! All right, so he's picking himself up and trying to dust himself off after hitting the car, and then he gets all of a sudden right about here he hears Mr. Softy. He's like, "Oh my God, Mr. Softy! It's up on the top of the hill." So he starts pedaling home, pedaling home, pedaling home, pedaling home. He gets to home, and then he keeps going past. He gets to Mr. Softy. He stops. He buys his ice cream, and then he gets on his tricycle and he pedals back home. All right, constant speed. So that's kind of a story. Okay. Um, you could do the same type of thing with velocity versus time. That is a lot trickier, right, than distance versus time. But if we did it with velocity versus time, we would have to have a straight line here, not a curve, all right, because we only deal with constant accelerations. So if this was a velocity versus time graph, if this was a straight line here, that would be constant positive acceleration, meaning he's getting faster and faster and faster. When he gets here, he's going with constant speed. And then here, he starts to decelerate until he stops. But this whole area here, the entire time, he's moving away. Okay? And now right here, you crossed over the line. So now, all right, you're getting negative, all right, displacement, or negative displacement. So this one, you're going forward. This area, you're going backwards. Here, you're going backwards with increasing velocity. So you're going faster and faster. All right. Here, your constant velocity. And then this area here, you're slowing down to a stop. But this whole entire time, you're going backwards. So if you looked at this area and this area, is he more forward? Let's say north is forward and south is backwards. All right. Since this area is larger than this area, he ends up in a net north location. Okay. All right. Graph overlays. Let's take this graph, distance versus time, and draw what a velocity graph would look like from this graph. And if you look, here's constant acceleration. So this is what constant acceleration looks like for a velocity. Here's not moving, so your velocity is zero. Here is a negative constant velocity. So this would be down here. Stopped again, zero. And then positive, it's going back home, right? Positive velocity, constant velocity. All right. Good job.